Hello and welcome, it's Mr. UMath again, and today we want to have a look at the Riemann functional equation. So what is the Riemann functional equation? Before we actually start with the proof, I just wanted to have a look at this kind of equation and show you where we want to arrive later on. So we have a pi over here and a pi over here. We have a gamma function over here and over here, and we have a zeta function over here and here. So the only difference between these equations you should have noticed is that there is one s here, here is one minus s, and all these complex variables of s are replaced by one minus s, and one minus s. Actually, what this should tell you is that there is some kind of underlying symmetry between the gamma function and the zeta function, which just is also relating the zeta function to its kind of symmetric function of zeta of 1 minus s. Okay, now another thing that you should notice is that we have again gamma multiplied with zeta. This should remind you of a previous video, and if you haven't watched it before, so please have a look at it. It is very important, the relationship between gamma and zeta function, because we are actually using very similar methods to derive this equation. Another video that you should have a look at is the Jacobi theta function that we also used, or better, we just tried to prove one functional equation for the theta function, for the Jacobi theta function, which will be important for this video. So if you want to be if you want to go sure that you know almost everything that you need for this video, please watch the previous videos. Okay, now as I told you, it seems to be a very similar proof, at least at the beginning, to the proof of the relationship between gamma and zeta function. So we should just start off with the gamma function. Remember that the gamma function of s is defined by the integral from 0 to infinity t to the s minus 1 e to the minus t dt. Okay, now if you remember the Riemann functional equation from the first slide, we didn't have s in the gamma function, we had s over 2. So let's just replace s over 2. So I will go ahead and replace s with s over 2, and remember that s is not the variable of integration, so we do not have to go ahead and substitute this dt by something else. We are just replacing the value here, s, by s over 2, and here and t we get t to the s over 2 minus 1. This e to the minus t doesn't change. Now in the second step we do something very similar to what we did in the proof for the relationship between gamma and zeta, but we are doing a little modification. We are not using the previous substitution, but a new substitution, which is t equals pi n squared x. Okay, now this should come or be familiar to you, because we use this kind of expression in the theta function. So we will somehow get the theta function. If you have a more precise look at this e to the minus t, we will get e to the minus pi n squared over x, or not over x but multiplied with x. Now what we will do in the next step is we will go ahead and implicitly differentiate this guy. On the left hand side we get dt, on the right hand side we get pi n squared dx. Okay, in order to find this, you could go ahead and just simply differentiate t in respect of x, and you would get dt dx, which would be just pi n squared, and multiply with dx, and you would get this. So let's just go ahead and replace all this stuff that we need. Now the left hand side didn't change because it was not depending on t. The right hand side, or better the integral, depended on t. So we replace this t by pi n squared x with this, and we go ahead and replace this t in the exponential with pi n squared x. Remember that we also have to replace dt by this differential expression by pi n squared dx. Now, what can we do with that kind of expression? We will just go ahead and, okay, I've just rewritten where we were. And in the next step, what I will be doing is I will be dividing with pi to the s over 2, and this will come to the left hand side, and n to the s, which will become 1 over n to the s here. Now you see on the right hand side we are left with this kind of integrand, which is an integral from 0 to infinity. What we will do in the next step is we will sum over all the natural values, so 1 to infinity. Why do I do this? To get here, for this expression, I will get the zeta function, and on the right hand side, if you have a look at this exponential and this sum, they will be somehow related to the Jacobi theta function, but not that is not equal to the Jacobi theta function. You will see soon. So what I'm doing now is, because these guys are constants, I can take them out of the sum. This is easy. So I have pi to the n, pi to the minus s over 2, gamma of s over 2, and the sum of 1 over n to the s, going for all the values from 1 to infinity, which is nothing else but the zeta function. Remember, on the right hand side we have interchanged the integral and the sum. You cannot always do this, but I assume that we can interchange them, and saying, or better assuming, uniform convergence of this kind of expression, or better of this sum. Now what I will do in the next step is I will have a more closer look at this kind of body, and I will just replace this by zeta of s. You see, we replace this by zeta of s, and now we have a look, or better, a real closer look at this guy. It is important for us that this is very strongly related to the theta function, or better, the Jacobi theta function, but it is only the positive branch, if you want to view it in such a way. So just write down here this theta function. It is the sum over all integer values, so from minus infinity to 0 and to plus infinity. Why do I say this? To 0, it is important that if you plug in a 0, you will get e to the minus pi n squared multiplied with 0, which will just give you e to the 0, which is just 1. This is what we have here. But the positive branch and the negative branch, so all the positive integer values from 1 to infinity and the negative from minus 1 to minus infinity, are actually the same because of this n squared. So all the signs will be cancelled and will become positive. So we have 2 times the sum n to infinity, n from 1 to infinity, sorry, and e to the minus pi n squared x, which is now defined by Riemann. So we actually call this guy here the psi function, and we have 1 plus 2 psi x. Remember, or better, have a look at this guy. This is nothing else but the psi function. Why am I using this? Because now actually I can use the properties of the theta function while integrating. So let's go ahead and just replace in this right hand side equation. I will just replace this sum by psi of x. Nothing really fancy what happened, and you should see that this kind of expression equals to the integral from 0 to infinity x to the s minus 2 x over 2 minus 1 psi x dx. Okay, we will use that later on in the final step. Now let's have a further look at this integral which we had on the right hand side and divide this up into 2 parts. So we have the interval the interval from 0 to infinity, and we divide this into 2 parts, so from 1 to infinity and from 0 to 1. Remember, 1 to infinity, 0 to infinity, if we add them together we will have the same integral on the left as we have on the left hand side. But why am I doing this? Because of this kind of expression. I don't like it, and you should not like it. also. So let's have a look at this kind of expression and use this kind of expression which we know from the theta function. So what we know from the theta function is that theta of x is equal to 1 over square root of x of theta 1 over x. Okay, if we just translate it into the language of the psi function, we get 2 psi x plus 1, which is nothing else but theta of x, is equal to 1 over square root of x, is equal to theta of 1 over x, and this guy here. Okay, now the only thing is that I replaced in this equation 1 over x and just placed it for theta of x. Now if we solve for psi of x, which is pretty easy, we bring this plus 1 to the right hand side, we get minus 1 and divide by 2, and we will have this kind of expression. Now you should see 1 over square root of x psi over 1x. This is from this part 1 over x multiplied with 2 psi of 1 over x, and we divide this by 2, so the square this 2 will cancel. We have plus 1 over square root of x. If we divide by 2, we will get a 2 here, and we subtracted 1 and we divided by 2, we get minus 1 over 2. Okay, just replace this into this equation. It is nothing else but psi x replaced by this guy that we found earlier in this integral. Okay, now again, what can we do? It is looking very complicated, but actually is not that complicated. The important part is, if you have a look at this, these are only power functions which can be easily integrated, and this is actually what we will do. But first, let's have a look what happens here in the front. We are just multiplying out this guy, x to the s over 2 minus 1, with 1 over square root of x psi 1 over x. Remember that 1 over square root of x is nothing else but x to the minus 1/2. If you subtract from minus 1 1/2, you get minus 3/2. Okay, I hope this is clear. This is nothing else but the power law that I'm using. Now we have this guy multiplied with psi of 1 over x, and we have plus 1/2, because we have a 1/2 here and 1/2 here. This kind of expression, again, I multiply out these guys. So in front I get the same as here. I get x over x to the s over 2 minus 3/2, and we get minus x to the s over 2 minus 1, which is just this factor in front. Now let's split up this integral into 2 parts, because we can easily integrate the right hand part, and the left hand part will just be left for this moment. So let's go ahead and integrate this. It is pretty easy actually. It's 1 over s over 2 minus 1/2 x to the s over 2 minus 1 over 2. Just simply using the power law for integration. Minus 1 over s/2 x s over 2. Sorry. And the boundaries are 1 and 0. If you just plug these guys in, you will get pretty simple expressions. So for 0, for the lower boundary, these guys will cancel, or better, they will become 0. And if we plug in 1, we get 1 over s over 2 minus 1 over 2 and 1 over s2. And if we multiply this 1/2 in there, we get 1 over, so just this expression, we get 1 over s minus 1 minus 1 over s. And if you just bring them together, these both fractions, you will have this guy here, 1 over s multiplied with s minus 1. And the front part of the integral didn't change, but we will come to this step. So I just rewritten what we had. So we found out that this integral, which went from 0 to 1, and we had x s over 2 something, this is just what we worked on. Now I will do a little substitution, which should be clear to you, because this 1 over x is not good, or not very nice looking. So we will replace x by 1 over u. We get dx by minus 1 u squared du. and we will also have these boundaries. Look at this 1. If we plug in 1 into this guy, we get for again 1, and if we plug 0 into there, we get infinity. Okay, let's just use this. So x will be replaced by 1 over u, and here, because we are replacing x by 1 over u, we have u here, and this differential expression dx will become minus du u squared. And remember, we didn't change anything to this guy. This is not part of the integral, so it's just left as 1 over s minus 1. Now what can we do here? First of all, you see the boundaries are not that good looking from infinity to 1. We can change this by using this minus sign over here, and now I also do another step which should also not confuse you that much, but instead of working with u, I can just replace the integrand by x. Okay, this is the only thing that I did, and I use this minus sign in front of this to change the boundaries of this integral. Nothing else changed. Now let's rewrite this again. So we found out that from 0 to 1, x to the s over 2 minus 1 psi x dx is equal to this integral from 1 to infinity x to the minus s over 2 minus 1 half psi x dx plus 1 and over s multiplied with s minus 1. So let's plug this into this first step. What we did, we found out that if we had this pi to the minus s halves, I think, multiplied with gamma of s half multiplied with zeta of s was equal to this left hand side of integral. We splitted this up into two parts, from 1 to infinity and from 0 to 1. Then we used the functional equation of the Jacobi theta function to derive this guy, and now I'm replacing this part, this here on the right hand side, with this long expression. It looks long at this point, but is not that hard actually. So you see, we can express this integral from 0 to infinity x to the s minus 1 s halves minus 1 psi x dx by this expression, and the only thing is that I replace this guy by this equation. You should see that. Sorry. Now what we can do is, because we have the same boundaries, we can bring both these functions together, and I will do that. I will go ahead and merge these integrals from 1 to infinity. We have here the coefficient is x to the s over 2 minus 1 plus x to the minus s over 2 minus 1 halves, and multiply this with psi x dx, and we have this constant term over here. Now what can we do with that? Actually, I will do a little kind of a review of where we started. We actually started off by this. Okay, we showed that pi to the minus s halves gamma s over 2 zeta of s is equal to this integral. Okay, to the integral from 0 to infinity x to the s over 2 minus 1 psi of x dx. Now we found out this right hand side, even if it is more complex than the stuff that we had before, we can just write it down. Now you should notice something. This psi x over x. Why have I written this way? It is because I wanted. It didn't change a lot. So if you just multiplied, if you divide this by x and this guy by x, you will actually land here. But this kind of expression is much better, because now if you replace s by 1 minus s, here 1 minus s, 1 minus s, you will see that this s will be changed to 1 minus s, and this guy will become s. So this guy didn't change, and these guys don't change also. So where we arrive actually is that if I take this kind of function, and or better this left hand side, and I replace s by 1 minus s, this is actually what I did, I will have the same integral. So actually I cannot evaluate this right hand side, but I can tell you that this guy if I replace s by 1 minus s everywhere, I will have the Riemann functional equation, and this is where we stop. Okay, actually now you saw it took us a lot of mathematics. It was not complicated, I hope. It was pretty simple, but in Riemann's papers it's just about 4 or 5 lines of integrals. It's pretty hard to understand what he did, and actually in the English version, which is uploaded at Clay Mathematics, there is an error, and I wrote them but they didn't respond. Now actually this is the final, actually not the final. I hope to do more videos soon, but this is the video for the Riemann functional equation. I hope you have fun watching this. I know it was a little bit tedious working with all these integrals, but it's very, very interesting to see this appearing, and we are almost very close to the Riemann hypothesis, because if you look at this guy, this s and 1 minus s, you should see that 1/2 plays a very important role between these. Okay, if you just work with it, you see that 1/2, the real value of 1/2, seems to be the key to the Riemann hypothesis, not actually in proving it, but in understanding it, where Riemann had the idea and why he had this idea with this critical line of 1/2 for the real value. Okay, so if you guys have further questions, further comments, please comment, and if you like this video, please give thumbs up, and I hope to see you guys soon, and I wish you a happy new year and lots of fun with mathematics. So see you guys.